It's my pleasure to welcome Eriko Hironaka, who will speak to us today on Lamerz problem in dilatations of mapping classes.
I'd like to thank David for inviting me to speak here. I'm going to talk about, this is an expository talk mostly about Lamerz problem, which has kind of a wide perspective. And what I'm going to do is slowly sort of move that toward questions that are interesting in mapping classes. I didn't expect to have anybody, I thought I'd have mostly people who were not working in mapping classes, so that part of it is only going to be at the end and just very brief, but hopefully you'll get the flavor of what I'm talking about. So Lamerz problem is a problem about algebraic integers. And I'm going to start out by just giving a few references, just in case you're interested in learning a little bit more about this on your own. So Lehmer, in 1933, posed a problem about algebraic integers, which I will say in a few minutes. This is still an open problem. Later in the 60s, Salem did some work on kind of a specific version of this problem, a little bit more, narrowing the problem a little bit. And Boyd and Mossinghoff, Boyd in the 70s and continuing now, and also Mossinghoff lately, they've continued working on the problem, and Mossinghoff has a website. So if you're interested, he has a website sort of recording the latest results on Lamerz problem. What I'm interested in is sort of dynamical systems analog to Lamerz problem. You can actually completely formulate the problem in terms of dynamical systems of a certain kind, and that gives it, you can use then other tools. This idea was developed maybe first by Lynn, Schmidt, and Ward in 90, and there's a book by Everest and Ward called Heights of Polynomials and something. And also Dan Silver and Susan Williams have done work on dynamical systems and knot theory applications. As a special kind of dynamical system, you can get some dynamical systems from Coxeter systems, and so interesting work was done by Smith, also McMullen, and I'm not naming everybody involved. These are some of the key players to get you started. So this gives some dynamics and combinatorics and graph theory connections to Lamerz problem, and then mapping classes. So Leininger, Farb, Margalit, and others. So what I've mostly been working on is the connection, these connections to Lamerz problem and their connections to each other. Okay, so what is Lamerz problem? So let P of X be a monic integer polynomial. And so the roots of P are algebraic integers. And we can think of them as lying in the complex plane. Here's the unit circle. Here's 0. And so the roots will be sort of either outside or inside or on the unit circle. So what we do is we define the Mahler measure, or the exponential Mahler measure, to be the product of over the roots outside the unit circle of the norms of the roots. And we can also think, so for alpha, an algebraic integer, we can define the Mahler measure of alpha to be the product over algebraic conjugates of alpha outside the unit circle. And this is just the Mahler measure of the minimal polynomial for alpha. Okay, so the question is, given delta bigger than 0, is there a polynomial, a monic integer polynomial, or an algebraic integer, such that the Mahler measure is strictly between 1 and 1 plus delta. So this was posed by Lehmer in 1933. The Mahler measure incorporates two measures of complexity. So two for an algebraic integer. So one is or for a polynomial. So one is the maximum norm of a root, or if we're talking about algebraic integers, then the maximum norm of an algebraic conjugate. And the other one is, which I'll denote n of p, is the number of beta. The number of beta, so that p of beta is 0 and beta is outside the unit circle. Okay, so the number of roots outside the unit circle. Okay, then we have, so lambda of p is less than or equal to the Mahler measure, and it's less than, which is less than or equal to lambda p to the n of p. Okay, so somehow this number, this invariant of monic integer polynomials, or this invariant of algebraic integers, is sort of squeezed between these things. Somehow knowing about the size of these things and this gives you an idea about the Mahler measure. Now, it's easy to see that lambda of p can be made arbitrarily close to 1. So take p, so let's just take lambda of x to the d minus 2. Then this is just the dth root of 2. In fact, all the roots have norm dth root of 2. But the Mahler measure is just 2. So this goes to 1, but the Mahler measure is always staying big. So the question so what I'm sort of saying here is that you can make sure that, so lambda bounds the distance of the roots from the origin. So you might say, okay, I want to make lambda get small. Well, you can do that as much as you want. But when you do that, you might be making the number of conjugates that are also outside the unit circle big enough so that it makes up for it and the Mahler measure stays big. So Lamer's problem is asking what that balance is, basically. Okay, so here are some facts about these invariants lambda, m, and n. So the following are equivalent. Lambda p is 1. M of p is 1. And p is a product of cyclotomic polynomials. In other words, all the roots are roots of unity. Okay, so we eliminate these. These are the ones that we can eliminate. So we eliminate all polynomials which are products of cyclotomics. And once we've done that, then we ask the question, what's happening with the Mahler measure? Can it get arbitrarily small or not? Another thing that one can immediately see is that for fixed D, the minima are achieved. So lambda D, there exists lambda D, so the minimum of lambda of Q where Q has degree D, and M sub D the minimum of the Mahler measures. And these are both bigger than 1. So for fixed D, you can always minimize. So there are some actual numbers, lambda D and M sub D. And that's because, so this is not hard to show. That's just because if you bounded lambda D, so you can always find some example. You bound lambda D, then the number of polynomials with lambda less than or equal to that is going to be there's only going to be a finite number of them. So it's just a minimum over a finite number of things. So that's how you prove that. Okay, so those are some sort of easy lemmas. Okay, now current state of knowledge. So that's where this is. It's good I wrote this down. This polynomial, L of x, which is called Lamer's polynomial, has the smallest known Mahler measure among non-cyclotomic polynomials. So M of L is around 1.17. It's the smallest known Mahler measure, bigger than 1. And this is after searches by Boyd and Mossinghoff up to around more than 40, degree 40. It's been verified. So this
Sorry, is that the date? What's 40?
degree 40.
Oh,
Sorry.
degree 40, sorry. I was going to say.
Yeah, degree.
Did you do that by hand?
Yeah, degree up to degree 40. Yeah, sorry, degree less or equal to 40. Okay. So since in the definition of M sub D, I'm allowing non-irreducible things, you'd expect that m sub d is going to be well, it should be it's definitely non-increasing. It seems so far that it actually just stops at 10. So it's at pretty small stage. Okay, so properties of Lamer's polynomial. So the Mahler measure of this is actually equal to lambda L. This number is called Lamer's number. So the picture is, this is the unit circle. You have lambda of L here on the real line. It's reciprocal, and then everything else is on the unit circle. So it's this kind of picture. So also L is reciprocal, which I kind of just said. This reciprocal is defined as follows. P of x given a polynomial P of x, define P star of x to be x to the degree of P times P of 1 over x. And a way to say it visually is if you write down P of x, you write P star is just the same polynomial with the coefficients written in the opposite order. So if you look at this, you can see that this is a reciprocal polynomial. Turns out it's irreducible. It's an irreducible reciprocal polynomial. And that means that all the roots will break down into inverse pairs as well as conjugate pairs. So, it's closed under inverses as well as conjugation, complex conjugation. So this special polynomial with the small Mahler measure has the property that it just has one root outside the unit circle. So the question is, if we push this in, if we try to make this smaller, does that force there to be more roots outside the unit circle? Now one might ask, well, what about non-reciprocal polynomials? It's interesting that in Lamer it actually developed computers. He was one of the people who pioneered the construction of computers and computer algorithms. He actually physically made computers to make computations. And he made a list of polynomials with small Mahler measure up to degree 10. And they turned out to they all do give the smallest Mahler measure in those degrees. And they were all, he doesn't explain why, but he looked at he only looked at even degrees, and he only looked at reciprocal polynomials. But it wasn't until 1970 that, at least in terms of results that were published, Smith showed that for P non-reciprocal, so irreducible, non-reciprocal, m of P is bigger than or equal to the Mahler measure of x cubed minus x minus 1. It's degree 3, which is around 1.32. So it's bigger than Lamer's number. And so this implies that to solve Lamer's problem, it suffices to look at even degree reciprocal polynomials. So, okay, and then one more definition. So I mentioned Salem in the beginning. If alpha is an algebraic integer and it satisfies that the Moller measure of its minimum polynomial is equal to lambda alpha, and P alpha is reciprocal, or alpha is algebraically conjugate to alpha inverse, we say alpha is a Salem number. This is not the usual definition, but it's equivalent to the usual definition, except possibly in degree 2. So the quadratic ones are also called piezo numbers or PV numbers. So these are the special cases when you have just one root outside the unit circle, one root inside the unit circle because it has its reciprocal, and then all the rest are on the unit circle. So open questions that many people have been working on, but there's still don't seem close to an answer. So are Salem numbers bounded from below by a constant bigger than 1? If minimum Moller measures for degree D eventually stabilize, to some Moller measure of some polynomial. Okay, so if we've solved Lamer's problem, would that be a Salem number? Okay, so is the answer going to be something with lots of roots outside the unit circle, or does somehow that balance have to be that there's only one root outside the unit circle? And I think this is not known. Is the minimum Moller measure always a Salem number? So far, I mean, I don't know if this is. I know that a lot of the. So, for example, up to degree 40, a lot is known about. There's a lot of computation. There's a lot of data on this, but I'm not sure exactly if this is true. Does anyone know that? Okay, so there's a lot that's not known. So I'm going to go to an easier question, hopefully easier question. What is the behavior of this? So this is the radius of the roots to the dth power. So if this is the minimum radius excluding 1, and you take the dth power, how does this function behave? So a weak version of Lamer's problem is the lim inf of with d going to infinity of lambda d to the d bigger than 1. Okay, so it's not hard to see.
What is lambda d again?
It's the minimum lambda of p, where degree p is d. Okay. So it's not hard to see that the weak Lamer's problem, if the answer is no, implies Lamer's problem to be yes. Okay, so it seems like there are a lot of, so if the lim inf is 1, if this gets close to 1, then that'll force the Mahler measure to get closer and closer to 1. That's basically. And so you just, you have this sequence of inequalities. So lambda sub d is less than or equal to m sub d is less than or equal to lambda of some polynomial of degree d to the number of roots outside the unit circle. This is the better bound. But certainly this is less than or equal to lambda sub d to the d. And we know that this is less than or equal to 2. Because if you take the polynomials x sub d minus 2, then to get that. So the lim sup, the lim inf and actually the lim sup, these things exist, so it would be interesting to know what they are. Now, those of you, a lot of you in this audience will kind of understand why I'm thinking about this, because this is very analogous to something that people work on in mapping classes. So I'm just kind of reframing it in the more general setting of algebraic integers. So there's an analogy in the theory of mapping classes. So algebraic integers.
I don't quite, and maybe I don't know which conjecture, what means yes and what means no.
Okay,
So what is a yes answer to Lamer's problem?
Lamer's problem, the way it was, he actually stated it, asked if you can always, for any delta, find a Mahler measure which is within.
So we conjecture the answer is no.
Right.
What people might call Lamer's conjecture is LP no.
Yeah, it's actually it's the
In fact,
opposite.
more strongly that Lamer's polynomial achieves them.
Yeah. Mm-hmm. Right, so the conjecture is the opposite, right? The conjecture is actually, the conjecture is that LP will be no, and that would imply that WLP would be yes.
So you might try to prove the weak Lamer's problem is yes.
Yeah, as a weaker, it wouldn't prove Lamer's problem, but at least it would support it. So that's why it's a weaker conjecture question. Okay, so there are some analogies going on in the background of all this with the theory of mapping classes. The algebraic integers correspond to a mapping class. This is just a homeomorphism from a closed oriented surface of genus G to itself.
Is this weak Lamer's problem open?
As far as I know, I know. Yeah, I think the kinds of inequalities I've seen haven't posed a question like this. It hasn't tried to look at it this way. There are bounds on, Mahler measure. See, this kind of thing, if you can get any kind of bounds on this, then you're going to get upper bounds on the Mahler measure. This goes to 1, so this doesn't help much. But this side, there's a question of, you know, if it's getting really small as d goes to infinity, that's evidence against the Lamerz conjecture. So if somehow we can find examples that seem to make this small, then that would settle the question.
So if I understand right, WLP is, I mean, it's just, an exactly equivalent question is, if you take a d by d integer matrix whose spectral radius is bigger than 1, can you make its spectral radius 1 plus epsilon over d?
Mm-hmm. By, yeah.
Right? I mean, the lambda is the same, the set of lambdas that arise is the same as the spectral radii of integer matrices.
Yeah. Of dimension d. Yeah. Right. Mm-hmm. Yeah, so I think it's an interesting question in itself that, you know, one can play with polynomials and get these kinds of sequences, you know, and sort of get some, I mean, this on its own is kind of, I think, an interesting sequence to look at. And people studying mapping classes have thought about this analogous thing quite a bit. So on the other hand, they're looking at special algebraic integers. But I think it's interesting to just pose the question for algebraic integers. See, maybe, you know.
So, I mean, following up on that, doesn't that Dan's paper have a proof that, I mean, if you do positive matrices, d by d matrices, then this is true. The spectral radius can't be 1 plus epsilon over d. I mean, you know how to make a positive matrix whose spectral radius is just barely above 1, but it's as close as possible. Right? You take a cyclic graph and add 1. Isn't this a lemma?
I bet they can't hear you in the video. But that's... okay. So I've been kind of talking about this analogy. Let me try to write it down. So let phi be a homeomorphism from a Riemann surface of genus G to itself. And we look at it modulo isotopy. I'm not going to... Orientation preserving, yes. Orientation preserving. Here we're interested in the non-cyclotomic ones. Non-cyclotomic algebraic integers. Here we're interested, by the Thurston-Nielsen classification, phi can be either isotopic to a periodic map, reducible map, so it sort of reduces to smaller genus, or sort of a general type map. And that's known as a pseudo-Nosov map. And it has the property that there's an element in the isotopy class, a unique element, which preserves invariant foliation. So basically, with singularities. But outside singularities, there are foliations so that the map expands by number lambda and contracts in the other direction by its inverse. So there's some associated number lambda, which is kind of the average of the distortion that's done by phi over the surface. And this is some constant bigger than 1, and that's called the dilatation. So there's this invariant called the dilatation. Dilatation of phi. And that corresponds to lambda alpha, the largest algebraic conjugate of alpha. And then here, when we fix degree, we know that we can make that there's some minimum bigger than 1. Similarly, if you fix the genus over here, there's also a minimum bigger than 1. And that's, so one reason is just, is a fact due to Thurston that ties this together, is that these numbers, lambda, are algebraic integers of degree 4g less than or equal to 4g minus 3. And it's also known that they're Perron numbers. That means that if you draw this picture, there's one real, so lambda is this real number. The rest of the algebraic conjugates are all strictly smaller in modulus than that number. So these are special algebraic integers, and they have degree that's bounded in terms of a linear function in the genus. So these things I've been talking about algebraic integers, you can ask the same thing about mapping classes. Actually, it went the other way around. A lot of people have asked it from this point of view. So let delta sub g be the minimum lambda phi, so where phi is a pseudo-Nassau mapping class on a surface of genus G. Now, because we're looking at mapping classes, these are geometric objects. These things have nice interpretations. So one of them, just to mention, delta G is or log of delta G is the length of the shortest geodesic with respect to the Teichmuller metric on the moduli space of curves, complex curves of genus G.
You see if I follow for G for 1, is that the golden ratio? Sounds good.
Well, no.
No, it's not. It's not. Because it's not.
Plus the square root of 5 over 2.
Yeah.
It's like for
Because
the,
it
for,
has
for,
to
the,
have-
for the figure 8 part, right? The one over the figure 8 part?
Right, 2, 1,
2,
1,
1,
1.
1.
Yes. Right. Yeah. Yeah. That's
It has
it.
to have norm 1, whatever the integer is.
Yeah. And there are other interpretations of delta G. Let me just make another example of how there is geometry associated to this. There's a recent result that says the mapping classes phi with small enough dilatation well, actually, sorry. So mapping classes define 3 manifolds as follows. You take your surface, sigma g, across the interval, and you mod out by x0 gets identified with px1. So this is a mapping torus. So given a mapping class, you have an associated mapping torus, so it's some 3 manifold. And so Farb, Leininger, and Margalit showed that if you take out the suspension of the singularities where the foliations weren't defined, so if you do a little bit of, you take out some small extra stuff, then n phi, if phi is small enough, then n phi must lie in some finite set. There is some finite set of things which admit the small the mapping tori of small dilatation maps.
By small mean delta of the dilatation of T is small?
So it's close to delta, at least. Delta G is the minimum. So there,
So,
yeah, maybe I should say a little bit more here.
so what does phi mean? It's only lambda.
So it's known that there is a smallest delta G, smallest dilatation for any genus. It's also known that this is by Penner. This is asymptotic to 1 over G. So so we know that delta G should be sort of bounded by constants times 1 over G, and Dan is here, so he can explain this better. But so based on that, if the dilatation is small, within the expected amount, roughly speaking, then the mapping torus must be equal to one of these
But the
finite.
notion of small depends on G. Yes.
Yes, exactly right. So we know this. We have this sort of estimate, and then if it's small compared to that. So there are some. So this geometry. This is putting a lot of restrictions on what delta G can be, because somehow this finite collection of manifolds is giving you all the information. So maybe if you understand this finite collection of manifolds, then you should be able to, you have the information to find out what delta G are. Exactly.
So all these manifolds are hyperbolic, right?
Yes.
And so can you compute their volume?
What is known about, I mean, so far it's kind of the argument was based on sort of triangulations, kind of.
Yeah, so the volume is small.
Yeah.
So if you say the pseudo, yeah. So all these three manifolds have small volume, but yeah, I can't give you a good. It's not we don't have a good estimate.
But I think that all this shows, I think, that the answer should be soon. Somehow we should be able to get this in the near future. I think there's a lot of hope for that, anyway, to solve this problem.
Which problem?
The mapping class version of Lamer's problem.
Which is?
Which is, okay, so we know this is true. So the question is, what is the behavior of delta G to the G? Okay, so this is analogous to that lambda sub D. And the weak, so this is sort of the weak Lamer's problem applied to mapping classes.
But the Penner thing says weak Lamer's problem is the answer is yes.
Yeah, actually,
This
right. So this is,
lambda
right,
is
so yeah,
positive.
that's true, that's true.
Bigger than 1.
Yeah.
I think you want a delta G approximately 1 plus 1 over G, or log delta G. Log delta G is about
Oh,
1
yes,
over G.
yes, yeah.
Otherwise, you don't want to take these small numbers, raise them to G power, and
Yeah.
try to get them bigger than 1.
Yeah. Okay, so this is the analogous question to Lamer's problem that I think is still open for mapping classes, and it's so one kind of question involving delta G is just to find delta G, but another one is to just sort of see what's the behavior of this thing. Delta G itself is only known for delta 1 and delta 2. For G equals 1 and 2, the number delta G is known, but for G bigger than that, it's not known.
Can you just go
Yeah.
back up in this analogy? If the genus corresponds to half the degree?
Yeah, roughly. Usually, yeah. But it could be worse. But
Because here you just look at even degrees, right?
Yeah, yeah.
Right.
Mhm.
So this polynomial corresponds to the surface of genus 5. So is that
yes,
somehow-
yes, and that's known, right. So Lamer's number itself appears as the dilatation of a pseudo-Nosov map on a genus 5 surface. Yeah. So this number is realized.
So what's the math?
There are different ways of describing it. One is that you take the -237 pretzel knot. So that's, and then 7 of these. Pretend this is 7. And then you go like this. And then you look at this. This surface is a fiber of a vibration. Yeah, and the monodromy gives you that dilatation.
And is L of x the Alexander polynomial? Is not?
It is, except actually L of minus x is the Alexander polynomial of this knot. Yeah. And this was actually written down in Reidemeister's book from 1932. And one wonders, it's kind of interesting that this Lamerz paper came out in 1933. So around the same time, this polynomial appeared in completely different contexts.
But do you mean Reidemeister wrote down Lamer's polynomial?
He did, except he wrote it with the minuses. I mean, he wrote, yeah. Yeah, but you can find it in his knot theory book, just as an example of an Alexander polynomial.
But did he pose Lemma's problem?
No, I mean, no mention of, just this is an Alexander
But
polynomial.
of all the knots in the world, he just said,
Let's take, say,
minus
yeah,
257
exactly.
pretzels.
Okay, so people have studied this delta G. The Penner found lower bounds and upper bound, lower bounds using the sort of algebraic considerations, and an upper bound by constructing examples. And then since then, Bauer, Minakawa, and King and I have constructed examples to get the bounds better. And so the best current bounds are 2 to the g over 12g minus 12 is less than or equal to delta g to the g is less than or equal to 2 plus square root of 3. So actually, this makes me wonder, is this number bigger than or equal to, or less than 2? It doesn't, it seems...
I just want to look for examples. Examples by computer.
You can just try to... The idea is that you're looking for examples where there's small distortion. So they should be defined by something simple. Something close to being periodic, but not. So you take a periodic thing and slightly tweak it, or, So there are lots of different ideas about how to construct simple things. And then that's been my approach, so then you get some examples.
How do you compute this distortion? Do you compute the largest eigenvalue of the mapping using homology?
That gives you, that only gives you a lower bound for the dilatation. You have to, one way to do it is to there's this train track algorithm that.
So you cannot just look at homology.
No, you can't just look at homology. But that's also an interesting thing that I'll talk about in a second, actually. The case, there are cases when it's just a matter of homology. I mean, for example, this one, the Alexander polynomial is the same. The largest root of the Alexander polynomial is the dilatation. And that's because the action on homology, the dynamics of the action on homology is the same as the dynamics of the map itself, the geometry of the map itself. But that's not always going to be the case. So
then, how about the opposite? I mean, can you just look at can you reciprocate the Torelli group and look at the infinum there?
well, so that's an interesting recent result also by Farb and others. And Margaret, and I'm not sure if there's another. Okay, and Lang. Okay, that if you look in the Torelli group, or sort of if you look in that actually the dilatation has to be larger. It kind of in the limit, there's a lower bound, right? You can't, so in
There's a lower
general,
bound period, right?
There's a lower bound.
there's a lower
So
bound. Oh, yeah,
log of delta G is 1, is equivalent to 1
Yeah.
instead of 1 over G.
right. So it should be that the oriental ones somehow give you the smallest dilatations. Orientable meaning that yeah, so sort of philosophically one would think that the orientable mapping classes, the ones where the homological dilatation is the same as the geometric dilatation, should give you the smallest delta G. But I don't know that that's completely well understood. So since we mentioned it, so there's a class, a subclass of mapping classes called the orientable ones. So phi is orientable if the invariant foliations are orientable. And in that case, the geometric dilatation, which is the phi I've been talking about, is equal to the homological dilatation. So among these, so one can ask, what's the minimum dilatation among genus G orientable mapping classes? So recently, Leno and Tifo gave some lower bounds for this in small genus and a conjecture about what the lower bound might be in higher genus. The lower genus examples work very well and give you exact answers for this number. So so just to, so Leno and Tifo, just to give some of their results. When G is even, delta G plus, so G is even and equal to 2, 4, 6, or 8. So I guess I didn't need to say this. When G is 2, 4, 6, or 8, delta G is bigger than or equal to the largest root of the polynomial, call it LT sub G, is x to the 2g minus x to the g, 1 plus x inverse plus 1. And then they conject, so they found them one by one, but they all have this form. So then they conjecture that if we call this eta g, they conjecture that delta g plus is bigger than or equal to lambda eta g for g even, for all g even. Now for g equals 2, as I've said, delta g is known. So delta 2 is known.
And is eta g realized in every genus by a student also?
Yes, I was
Oh.
In fact, that's my, yeah. So delta 2 is known due to Cho and Ham, and that happens to be orientable. So then it's known that there is that these are equal, and it actually equals that. So in genus equal to 2, this has been verified. For G equals 4, 6, and 8, they're giving this as a lower bound. Then in genus 4 and genus equal to 4, they actually find an example that gives you that number, eta G. So delta G plus actually equals, delta 4 plus is equal to eta 4. So proof by example. For 6 and 8, they just have it as a lower bound, and then there's a conjecture after that. So I'll just finish with
You know you started late, right?
okay.
You started at least 10 minutes late.
Okay, well, so I'll just finish with this last this theorem. So there exists, to answer Dan's question, so there exists a map so I can find an example which is orientable when G is even, but not orientable when G is not even, when G is odd. So that lambda of phi sub G is equal to eta G.
For every G?
For every G, for all G. So this proves
Who's that due to?
to me so this proves because this lower bound is actually proved for 6 and 8. So this proves that delta 6 plus is eta 6 and delta 8 plus. So modulo the conjecture, you also might conjecture that these are equal. That their conjecture implies that these would be equal for all G. That delta G plus. So, well, it's the same. Yeah, actually, I shouldn't have said this. It's really this. Their conjecture is that this is equal. So this gives support to that conjecture. What it also does, if you look at the polynomial, is it shows that for all G, 3 plus square root of 5, well, so delta G to the G is less than or equal to 3, for all epsilon bigger than 0, 3 plus epsilon plus square root of 3 plus epsilon squared minus 4 over 2. So this is a easy exercise. So in other words, when you take the lim sup, you get 3 plus square root of 5 over 2 of delta G, sorry. Delta G to the G. And maybe I should just mention some of the other numbers. For odd G, Lano and Tifo also find bounds for actual values for delta 3 plus and delta 5 plus is Lamer's number. So, so these are known, and this is equal to eta 3, and this is strictly less than eta 5. So one might also conjecture that this is less based on any examples, but just one might hope that delta G plus is always less than or equal to eta G for all G. So with equality, when G is even. So that's.
Well, thank you. There were a lot of questions already, but are there more? Got lots of time. They're not expecting us for dinner for 20 minutes.
Can you say anything about what these look like?
So they really just, I mean, I can say some things about it, like something about the singularities and things like that. But I haven't completely worked out.
That's the 3 manifold.
But the 3, yeah, that's enough. Yeah, I should have mentioned also. Small dilatation things are supposed to just come from a finite set of 3 manifolds. These 3 manifolds should be fairly simple. So these ones come from S3, oops, wrong stroke. S3 minus a certain link. And it's, I hope this is right. It's either this or similar, but and if this isn't right, it's meant to be the 622 link. And if you look at this and you look at the
So what does this correspond to?
so this is a manifold,
Yeah.
and so H1 of it, this has 2 components. Should have 2 components, and so it's first homology is Z cross Z. So it has lots of potential ways to fiber. It turns out that there's obviously lots of symmetry. It turns out that there's the Thurston norm ball. Thurston norm ball tells you that if you're on if there's a fibration on one point of a face, then all the points will correspond to fibrations. All the rational points will correspond to fibrations. So, so basically, these examples come from one fibered face.
So for every G it comes from this field?
Yes, from just this one.
So your conjecture is that it's all from one grid.
Well, these I mean, you can compute because this is really. So this point here, there's a point here which corresponds to the mapping class that corresponds to this braid. So if you can also think of this link as, you can also draw the link like this. So there's an obvious fibration that comes from the braid. So there's obvious mapping class that comes on the 4 times punctured sphere coming from the braid, and that corresponds to this point on the fibered face. And if you do McMullen's construction, where you take the Z covering associated to the fibration, then you take a Z covering associated to an invariant element of H1, then you're going to get, from there you can construct a family of fibrations of this manifold. And So on this picture, it corresponds to looking at these points.
But don't you want the fiber to be closed manifold? Is you're gonna get
In-
close
in-
up somehow?
In the Farb, Leininger-Margolid paper, that result, they had to take away the suspension of the singularities anyway. So you want to take, your manifold is going to be something with some tori removed. So this is a very plausible example. Is that your question? I mean, you can always
No,
take.
he's wondering where are the closed surfaces? How is the genus going to infinity?
Okay, so
Now you are in mapping class saying, no, it's two functions.
right. So you look at the z covering of this thing, and then but then you take another covering of the surface, and you take the covering of so this is, say, sigma plus r. You take a covering of sigma, so you get a new manifold here. And then you, so this has a z cross z acting on it. It turns out that z cross z, this thing here, in this case, is just the z cross z covering defined by H1. But in general, you can make a z cross z covering. Then when you mod out by something which leaves you a z cross z, so if you mod out by an ideal that, if you mod this by something that gives you z, then that's going to correspond to a map from pi1 of x to z. And so those give you different points on this picture.
Okay.
And
Those are all punctured discs, right? Do you have to take a double cover? Is it like a
no, you don't get. In fact, you don't get punctured disks. You get things of higher and higher
Oh, you
genus.
do, okay.
Yeah.
So, but do you really look at the link complement, or do you do like surgery on the link to get a closed manifold? It's just a question of the boundary level. Well, that's me.
What you're going to get is surfaces with boundary components, but the surfaces have higher and higher genus. So you don't just keep getting the disk minus some points. You get surfaces of higher and higher genus minus some points.
Okay.
In fact, you get surfaces of higher and higher genus minus 4 points always in the examples I'm looking at. Hold it. Sorry, no, I mean 2 points. So you always get some sort of singularities of the vibrations that you need to get rid of. Anyway, I'm not explaining this well.
Well, so, I mean, if I can just recapitulate what you said, this link comes to you presented as a vibration over the circle with fiber of 4 times punctured disk.
Yeah.
So genus 0, 4 punctures. But if you perturb that vibration slightly, you get something with high genus with some number of punctures. So that gives you monodromy on a punctured surface.
Mm-hmm.
But it turns out those punctures are irrelevant from the point of view of the pseudo-anosov because they're zeros of the foliation.
Right.
So you fill them in and the dilatation doesn't even go down. And it's still realized by the action on homology, and those are your examples.
Right. So maybe it's a little bit confusing because on a disk, of course, if you filled these in, your mapping class is trivial. It's not giving you anything interesting. But if you have a higher genus thing, even with punctures, filling in the punctures might not change the minimal the minimal entropy model for the mapping class.
And that initial disk is not even one of your dots, right? I mean, that dot is, the disk is that dot on the x-axis. And
Right.
the dots that give
Yeah.
you your examples
These ones
don't include it.
look different from from this, and that might be one. But and also, if you think about this is giving you these are the Thurston norm balls, so you can already see that the genus is going to go up.
So by the way, that's the 2111 mapping class, right?
Right. Yes, exactly right. So the first, although it doesn't appear here, but it's the 211 mapping class. This here has dilatation.
What's 111?
The one you were mentioning. It's
Oh,
a
the
small,
matrix one.
yeah.
Okay.
If you take the double
they're
cover
torus.
of this one, if you take the double cover of this one, you do get the minimal dilatation mapping class on the torus. But for these, we don't need to take double coverings. You just take the mapping class itself, and it'll give you the small dilatation. But I mean, I think there are lots of, I think this is just something that, it's not hard to compute the dilatations because of the whole theory of Teichmuller polynomials that developed by McMullen. And so it's really a matter of noticing that the polynomials are matching up and things like that. But if you look at it, you can say things about the singularities, you can say things about what the action is and what the genus is and things like that, the fact that it's orientable and so on. So it's really worth, I think, studying. And it would be interesting to know, for example, in the genus 2 case or the genus 4 case, how does it compare to previous known examples, minimal examples for genus 2 and genus 4? And that I haven't had a chance to work that out yet.
Are there more shorter questions?
Is there a plane curve singularity in the background?
That's interesting. I mean, in the -237 pretzel knot, it's somehow related to some singularities. But yeah, I don't know. That would be nice.
Any other questions? They don't really have to be short.
Just
Okay,
a
go for it.
philosophical question. I mean, so does any of this stuff at the end kind of help you solve the initial number theoretical problem?
Actually, I was wondering if, just having examples like this x to the 2g minus x to g, this kind of suggests an approach to Lamer's problem that you just, because we're interested in even genus and reciprocal polynomials. So what about just things like this? Where this is some fixed reciprocal polynomial, something in x plus x inverse, and then you let g go to infinity and see what happens. That at least gives you some bounds. I wonder if you can get some interesting bounds. And the thing about the way I get bounds for this is you just look at this as a quadratic polynomial, and then you just say, well, if you can bound this, then you have a bound on the root. So sometimes things that come up from geometry might suggest, I guess, examples. But on the other hand, I think they're pretty far apart. I think.
Well, here's a concrete question.
Yeah.
Okay. So in this dictionary that you said kind of led to many of these definitions.
Yeah.
How about this orientable versus non-orientable dichotomy? Does it happen in number theory?
Well, I think something that might be a little bit just philosophically, not so much, but it's sort of mysterious still to me why you want to look at reciprocal polynomials. Yeah, I mean, there's a proof, and you could follow but the fact that sort of reciprocal polynomials give you smaller Mahler measure, or possibly that having just one root outside the unit circle gives you smaller Mahler measure, which is kind of counterintuitive almost, This seems analogous a little bit to how in mapping classes you actually want the orientable mapping classes. The orientable mapping classes seem to be giving you the smaller dilatation. It seems like you're putting more conditions on, but those are giving you the better answers. So sort of philosophically, it just seems like there's a question about, what is, you want to minimize complexity somehow. It's not just some brute force making something small. It's like there are all these different factors that can make the algebraic integer or the mapping class more complex. And if you somehow the smallest Mahler measure or the smallest dilatation seems to be associated with things with small complexity overall. And so I don't know. So I guess in that kind of sense, if you can identify something as maybe an added complexity, then you can try to eliminate that to get smaller and smaller.
So
Mahler
just a
measures of
comment
dilatation.
that, the characteristic polynomial of a general matrix is just a general polynomial. But for a symplectic matrix, it's a reciprocal polynomial.
Yeah.
And so the action on homology is per force having a reciprocal characteristic polynomial.
Well, maybe we should stop here. Thank the speaker again.